An orbital has n is equal to 3. Okay. What are the possible values of L and ML? Please remember, when n is equal to 3, what are the formulae? Well, when n has a value of 3, it can begin from 0, 1, 2 till n minus 1. This is the generic formula for L. So in our case, possible values of L are 0, 1, 2. N minus 1 till n minus 1. So till 3 minus 1, 2. So L can have value 0, that means S orbital. 1 means P orbital. And 2, that means D orbitals. Yes. Right. ML. What is ML? It varies from minus L till 0 till plus L. All integers. So it could be M can be minus 2, minus 1, 0, plus 1, plus 2. Any of these 5 values. Each of them is a valid number. List the quantum numbers ML and L of electrons for a 3D orbital. For a 3D orbital, well, L is equal to 2 for a D orbital. Fine. Now, 3D can have different orbitals. We have d x square minus y square, dz square, dxy, dyz, and dxz. There are 5 different d orbitals. 3D, 4D, whatever, there are 5 types. And L is always 2 for them, for any d orbital. For any d orbital. L has a fixed value 2. What about ML? ML can be 0. Yes. It can be plus 1, minus 1, plus 2, and minus 2. So 5 different values for ML are possible. Which of the following orbitals are possible? Now, is 1p possible? No, only 1s is possible. 1p is not possible. 2s and 2p are possible. 3s, 3p and 3d are possible. 3f is again not possible. 2d, it is not mentioned here, but 2d also is not possible. So, well, first and last are not possible, second and third are very much possible. Using SPD notations, describe the orbital with the following quantum numbers. Well, n is equal to 1, L is equal to 0 represents 1s orbital. Lovely. N is equal to 3, L is equal to 1. It represents 3p orbital. N is equal to 4, L is equal to 2 is 4d. Because L is equal to 1 is S, L is equal to 0 is S, 1 is P, 2 is D, and 3 represents F orbital. So these are the respective notations. Explain giving reasons which of the following sets of quantum numbers are not possible. Well, n is equal to 0. N is equal to 0 is not possible. That means 0th shell. No, it has to be at least 1 and begins from 1. So, since reason is n can have a value greater than or equal to 1, it cannot be 0. This is not possible. N is equal to 1, right? L is equal to 0. Yes, it is 1s. ML can have only one value, which is 0. Yes. And MS can be plus half or minus half. It is minus half. Is it possible? Yes, it is possible. No problem. N1, L1. Now, this is bad. L can have values from 0 till n minus 1. So, for n is equal to 1, L can only have a value of 0, 1s. So, these are really, nothing to comment on this. L is wrong here. So since L is equal to 1, not possible for first shell n is equal to 1. That is the reason for not having C. C is also a wrong option. N is equal to 2, L is equal to 1. That means 2p orbital. Is 2p orbital possible? Yes. ML can always be 0, spin can be plus half, minus half, no problem. It is quite possible, no issues. N3, L3, oh my God, this means F orbital. Please note, L maximum is n minus 1. The maximum L which is possible is 2. So since 3F is not possible, this is wrong. There is no need to see here. This is by itself wrong. N is equal to 3, L is equal to 1 means 3p orbitals. ML 0, okay. Spin can be plus half, minus half, anything. Is this possible? Yes. Alternate ones seem to be possible and impossible in this case. So this is it. How many electrons in an atom may have the following quantum numbers? Fascinating. N is equal to 4, MS is minus half. Now N is equal to 4, fourth shell, and spin minus half. Now the moment you have fourth shell, I can have 4s, 4p, 4d and 4f. Yes. Spin value is minus half. That means spin plus half also is possible within an orbital, but that we have to leave. So within an orbital, we can have only one electron with spin minus half. Okay. So this is 4s. N is equal to 4. Yes. Now L is equal to 1. Fine. In this case, L is equal to 2. Sorry, L is equal to 0. I'm so sorry. Just slip of tongue. I'll just correct this. L is 0, and in this case, L is 1. And in this case, L is 2. And in this case, L is 3. Right? Right. So we have N, L. What about M or ML? ML, for s orbitals, it can have only one value, 0. And spin quantum number can only be minus half, minus half, minus half and minus half. MS, you can say. So total number of electrons, four s orbital, only one orbital which contains only one electron with minus half, so only one electron is possible here. 4p, ML can be minus 1, 0, plus 1. It can have 3 electrons. D orbital, minus 2, minus 1, 0, plus 1, plus 2. 5 and minus 3, minus 2, minus 1, 0, plus 1, plus 2, plus 3. 7. 3 plus 1, 4 plus 5, 9 plus 7, 16. Well, I can have a total of 16 electrons, my dear, with these specifications. What about the case N3L0? L0 means this is a 3s orbital. ML can have only one value, 0. And MS can be plus minus half. Can be plus minus half. So 3s, only 2 electrons are possible, plus with 3, 0, 0 plus half and 3, 0, 0 minus half. Show that the circumference of Bohr orbit for the hydrogen atom is an integral multiple of the de Broglie wavelength associated with the electron revolving around the orbit. That's very interesting. Now, if you remember, Bohr's theory said that electron can revolve only in those orbits for which MVR is NH upon 2 pi. Yes. So, MV is NH upon 2 pi r, right? What is mv? Mv is nothing but momentum p, right? And for de Broglie wavelength, p is h by lambda de Broglie. Oh my God, yes. What does that mean? That's very clear as daylight. So I can say now h can cancel, and I can say lambda de Broglie is simply 2 pi r upon n, or 2 pi r is n times lambda de Broglie. This is circumference of Bohr orbit. 2 pi r is circumference of a circle, which is nothing but a Bohr orbit, and that is integer multiple n times lambda de Broglie. It is integer multiple of the de Broglie wavelength associated with the electron. There we are, and it fits in so beautifully, and that's how we see that there is, although unintentional, but a consistency between Bohr's theory and de Broglie's proposal. What transition in the hydrogen spectrum would have the same wavelength as the Balmer transition 4 to 2 of He plus spectrum? Now this is what you call a good question. We are trying to match energy differences or wavelengths. What transition in the hydrogen spectrum? Now we don't know N1 and N2 for hydrogen, but then I am given would have the same wavelength. Now wavelength is same, and I have a formula. 1 by lambda is RH Z square 1 upon N1 square minus 1 upon N2 square. And since lambda is same, so I can say this is equal to RH Z square 1 upon N1 square minus 1 upon N2 square. This is for hydrogen and this is for helium. Okay, very good. Can I simplify? Yes, beautifully things cancel out. Rydberg's constant gets cancelled. Yeah. And what transition in hydrogen spectrum? So essentially, I am asked N1 and N2. This is what is being asked. Now ZH is 1. So 1 upon N1 square minus 1 upon N2 square in case of hydrogen. This is 1 square, so there is 1. This is, now, if you look at this, I could also write it as 1 upon N1 by, now Z, this is equal to 2. For helium, Z is 2. What have you done? See, I'll just explain. I'll just erase it in fact and explain it again because I think I've written it very quickly. Yeah. See, it's going to be like this. Balmer transition of 4 to 2 of He plus spectrum. Now I know that this is given to me as 2 and this is given to me as 4. Fine. And Z also has been given to me as 2. I'll just substitute. What do I get? 2 square. 1 upon 2 square minus 1 upon 4 square. Right? This is for helium. I'm substituting for helium. Could I just take this 2 square in? I can. The 1 upon 1 square minus 1 upon 2 square. It becomes like this. Oh wow. Just look at this. 1 upon 1 square. Just notice this. There's 1 to 1 correspondence. And there is. So if I put N1 as 1 and N2 as 2, will it match? Yes, it would match. And this is what is asked. Which transition in hydrogen spectrum? So from 2 to 1 in hydrogen atom. That means Lyman series. So I have a Lyman series transition. The smallest energy photon or the longest wavelength of Lyman series matches with this transition of Balmer series of helium cation. That's it. Calculate the energy required for the process. He plus gas gives you He2 plus gas plus electron. We are supposed to calculate the energy which is required for this process. Well, He plus is just hydrogen-like, right? And I'm supposed to ionize this. That means I'm supposed to remove electron from N initial is 1 and N final is infinity. You don't equate with infinities. Maths people will get mad, but it's okay. I mean, in chemistry we do all such things, and we understand why we are doing this with the limitations. The ionization energy of hydrogen atom in ground state, I am given E naught. Is 2.18 into 10 raised to minus 18 joules per atom, and E is E naught Z square by N square. Yes. And in this case, ionization energy required is energy final minus energy initial. What is ionization energy? The energy required to move the electron from first orbit of He plus to infinity, so that when it goes to infinity means it is lost, it is gone. There is no attraction. Final minus initial, which means E infinity minus E1. And this is for He plus. And E infinity is 0. At infinity, there is no energy. This is minus of E1 for He plus. And how much is this? This is minus of E naught into Z square upon N square. And 1 means N is equal to 1. So this is minus E naught Z square, because we are taking the electron away from the first shell to infinity. So N1 is 1. Yeah, N is 1. That is why 1. What is E naught? I am given. Okay, this is minus 2.18. So this is 2.18 into 10 raised to minus 18 joules per atom into 2 square. You just multiply the stupid thing by 4. That is it. 8.72 into 10 raised to minus 18 joules per atom. My dears, this is the ionization energy of He plus. And that's it. If the diameter of carbon atom is 0.15 nanometers, okay, calculate the number of carbon atoms which can be placed side by side in a straight line across length of a scale 20 centimeters long. Wow. So I have a scale 20 centimeters long, and I am being asked, fine, I will have one atom after the other, back to back, back to back, back to back, like that. I can go on. So how many can fit? Do you see that when I am just packing one atom after the other, and suppose there are n atoms, and this diameter is say phi. Say, so one diameter is phi, so n diameters are n times phi. Yes. And this is equal to total length L, right? So n is L by phi. Common sense. Don't be very scandalized by phi. You could also write D or something. That's okay. What is the total length? 20 centimeters. And what is phi? 0.15 nanometer. Oh my God, centi and nano, yes. Meter can cancel with meter. Oh, can we cancel them like this? Yes. Centi just means multiplied by 10 raised to minus 2. And nano means multiplied by 10 raised to minus 9. That's all. That's all, my dear. Wow, that's pretty easy. It is easy. What do I get? Well, a lot. I have 20 by 15, which is 4.3, which is 1.333 into 10 raised to 9 atoms. 1.333 billion atoms placed one after the other can complete the length. That is what is required. 2 into 10 raised to 8 atoms of carbon are arranged side by side. Similar question, very similar. Calculate the radius of carbon atom if the length of this arrangement is 2.4 centimeters. How emotional, how senti. Say this is the length. We have the lovely carbon atoms happily sitting one after the other till the length of, say what? We had 2.4 centimeters. Is n times, if radius is r, diameter is 2 times r. 2r, 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 n times. So n times 2r, which is diameter. And I'm given n this times, and I'm supposed to find r. How tough, how stupid. 2.4 centimeter divided by 2, of course, and n. What is n? This is n. Oh my God, that's it, my dear. And how much does that come out to be? 2 2s are 4, so 0.6 into 10 raised to minus 8 centimeter. Well, so radius comes out to be, 6 into 10 raised to minus 9 centimeter. The radius looks like 6 into 10 raised to minus 9 centimeter. It is given in meters, that's it. 10 raised to minus 9 centimeters, also 10 raised to minus 11 meters. Nothing simple about it, that's okay. One more common sense based questions on very similar lines. It says the diameter of a zinc atom is 2.6 angstrom units. Calculate the radius of zinc atom in pm. Now, we can't stoop lower than this. I'm given diameter. Oh my God, how tough it is. It is the height of stupidity. And radius is diameter by 2. Which is 2.6 upon 2. Oh my God, this is 1.3 angstrom units. Yes, this is so tough. This is so dumb. But yes, we have it. Let's take it. Second part. The number of atoms present in a length of 1.6 centimeter if zinc atoms are arranged side by side lengthwise. Same drama repeats itself. Length is n times phi. What is length? 1.6 centimeter. N I'm supposed to find. This is 2.6 angstrom units. So N is 1.6 into 10 raised to minus 2 divided by 2.6 into 10 raised to minus 10. How lovely that would be. 16 by 26. That makes it 8 by 13 into 10 raised to 8 atoms side by side. Right? There we are. If somebody has issues with division, that's different. Otherwise, you can just divide and get this nonsense. This is 80 into 10 raised to 7 if you want it. Now 13 6 are 78, 80, 20, 13 was a 13. 70, 13 5s are 65, 50, 13, roughly this much into 10 raised to 7 atoms. 61.54 million atoms, and that would be the answer. A certain particle carries 2.5 into 10 raised to minus 16 coulombs of static electric charge. Calculate the number of electrons present in it. Wow. Well, what is the charge on one electron? Charge on one electron multiplied by number of electrons, right? This would be equal to what? This would be equal to total charge on क्या चीज़ है वो species जो भी है. Given substance. So 2.5 into 10 raised to minus 16 coulombs. This is the total charge. And charge on one electron is 1.6 into 10 raised to minus 19 coulombs into N. So N is 2.5 into 10 raised to minus 16 divided by 1.6 into 10 raised to minus 19. How fascinating is that? This is 25 by 16, God bless us, into 10 raised to 3. electrons. I guess we could always be able to divide them. Yeah. So once we divide it, we get the right number, and this comes out to be 1560. These many electrons are present? Yes, they are present. In Millikan's experiment, static electric charge on the oil drops has been obtained by shining X-rays. Well, a lot of drama. Actually, Millikan's name, X-rays, how you obtained it, who cares? That has nothing to do with the question. It is just a facade to make you afraid, nothing more. Just listen. Just leave this first sentence. Go ahead. If static electric charge on oil drop, now this is something which is sensible, is minus 1.282 into 10 raised to minus 18 coulombs. Fine. And this is equal to 1.6 into 10 raised to minus 19 coulombs, which is charge on one electron into n, number of electrons present on the oil drop. So number of electrons will be, this is minus y, electronic charge is negative, that's why. So n will be 1.282 into 10 raised to minus 18 divided by 1.6 into 10 raised to minus 19. How lovely is that? And that comes out to be, you just have to divide 12.82 upon 1.6 or 602, whatever, you can count it. Now 16 8s are 128. So this looks like 8. Wow. That stupid oil drop actually contains 8 electrons. Yes, it contains 8 electrons. In Rutherford's experiment, generally, the thin foil of heavy atoms like gold, platinum, etc. have been used for bombardment by alpha particles. Fine. If the thin foil of light atoms like aluminum, etc. is used, what difference would be observed from the above results? We used gold, we used platinum, they were pretty heavy. Why not use something as light as aluminum? We could. Just that the nuclei of lighter atoms like aluminum would not be so massive or heavy, right? So when there is a head-on collision by alpha particle, the deflection of alpha particle would not be that enormous. Anyway, the deflection of alpha particles is very small. And the moment the radius of the charge on the nucleus becomes smaller for things like aluminum, the interaction is even poorer, lesser, and the deflection would be even more negligible or more difficult to record. That would be the observation for aluminum or lighter elements in general. Symbols like BR7935 and BR79 can be written, okay? Whereas symbols of BR3579 and BR35 are not acceptable. Answer briefly. Yes. Whenever we have any element, we can have any element here, right? On the top, we have atomic mass number. This is atomic mass number, which is N plus P, neutrons plus protons. And on the lower side, we have atomic number Z, which is also equal to number of protons. So this should actually have come down by convention. I mean, we are free to write whatever we wish. But on the top, this would mean atomic mass number, and bromine cannot have atomic mass number as low as 35. Why? Because bromine, what about the atomic number of bromine? Bromine itself has atomic number of 35. That means protons themselves are 35 and there have to be at least few neutrons. Now it can't have 0 neutrons. So if you write 35, either you have changed the notation, which you are not free to change, or the number of neutrons is 0 in bromine atom, which is absurd. That is why this is nonsense. Same here. You can't exchange and you can't write up and down things like this. The upper one has to be atomic mass number and the lower one has to be atomic number, because that is the standard convention, and because in these symbols we have violated that convention. These are wrong options. An element with mass number 81 contains 31.7% more neutrons as compared to protons. Assign the atomic symbol. How do we solve this? Well, it has mass number 81, okay, and there is some element E, fine, whatever it is. and it has mass number 81. That means neutrons plus protons is equal to 81. And it has 31.7% more neutrons as compared to protons. Can I translate this in mathematical equation? Yes. Neutron is more than proton. How much? 31.7% more. How do I write this? So neutron A, there are some number of protons? Yes. More means you add. More means in number of protons, I add something. How much do I add? 31.7%. Per means divided by, and cent means 100. So 31.7 upon 100 times protons. This if you add to what? If you add this to number of protons. Well, excellent. What do you get? You get number of neutrons. This is a part of the question itself. How much is that? This is 1.317 times protons. Wow. And I have an equation. I'll use that. 1.317 times proton plus proton is 81. So protons is 81 divided by 2.317. How loving. I do this, I solve this, and I get the atomic number. Can I get that? Well, it seems I can. How do I solve this? Well. It is just a piece of dirty maths. I can say you divide and get this. But the students say, we don't know how to divide such dirty numbers and we need a calculator. You don't get a calculator in exam. You should know how to do hand calculations. And luckily for us, number of protons has to be integer. You can't have decimal protons, right? So, let's give it a shot. 23 is stable, you may not remember. Yeah. 2317 is ugly. I'll just approximate it by 2.3 in denominator. 23. Let me check. 823 fours are. No, this is 92. It becomes a little too much. We're just having 81. So I'll just take 3 times. This is 69. Right. So can I say this is 69 plus 12 by 2.3 roughly. Why? That 17 I have just ditched. How much is this? This is 30 plus 12 by 2.3. Now suddenly an idea strikes me. Had it been 2.4, 12 by 2.4, how much that would have been? 12 2s are 24. So 1 by 0.2, that would have been 5. So had 12 by 2.4 would have been 5. Yes, that would have been how much? 1 upon 0.2, which is 5. Right. So yes, I get atomic number P as 35. 35 atomic number, that is bromine. So what is the symbol? The symbol is bromine 3581. Is this the answer? Yes, this is the answer. An ion with a mass number 37 possesses 1 unit of negative charge. That means whatever this ion is, let us say it is X, so it has -1 charge. If the ion contains 11.1% more neutrons, not atom, ion contains 11.1% more neutrons than electrons. That means if number of electrons is E, let us say if the number of electrons is E, the number of neutrons will be, well, neutrons will be E plus why? Because they have written more, 11.1%. What have you written? Very simple. See, I'm just converting this English language statement to maths. If the ion contains 11.1% more neutrons, more means I add, than electrons, so mean whatever is number of electrons, neutrons is at least that much, plus it is 11.1% more, so electrons, that number is there. At the same time, it is a little more also. How much? 11.1% means 11.1, per means divided by, cent means 100, so much. That gives me how much? Well, 1.111 E. That's roughly 10 by 9 times E. And let us not forget what? I'm given that it is a -1 charge. That means number of electrons is number of protons minus one, plus 1. For a neutral atom, protons is equal to electrons. For -1 charge, very naturally, number of electrons is 1 more than number of protons. Let us not forget, right? So, E is P plus 1 in case you need that. And atomic number A is neutrons plus proton. Sorry, atomic mass number. Mass number is 37, I am told. So 37 is neutrons. Neutrons is 10 by 9 E plus P. Now E is P plus 1. So 10 by 9 P plus 1 plus P. Can I solve this? Yes. 37 is equal to 10 by 9 plus 1, that is 19 by 9 P plus 10 by 9. But that's pretty fanciful. So I would say 37 into 9 minus 10 by 19 is equal to P. I have to solve this ugly thing. How is that? You are free to calculate if you wish. Multiplication by 9, subtraction by 10 is not difficult. Division by 19 also is unpleasant but not impossible. But I can approximate it also, and since I know that P has to be an integer, I can afford to do approximate calculation and still I would get accurate calculations. Do it with me and see. Mostly people leave it here. Na? Okay, fine, this is done, now you do it. Mathematics also is a very important part of calculations. So let us also try to see how do we calculate. Are there tricks? Yes, there are. Let's do that. I would rather say 37 is 38 minus 1 into 9 by 19. I would rather write it like this. Right? Minus 10 by 19. 10 by 19 is approximately 10 by 20, which is roughly 0.5. How much does this come out to be? This is 2 minus 1 by 19, or rather 9 by 19. 9 to the 18. Let me take it in. It is so much. Minus 10 by 19. Oh my God, I'm solving it very accurately. How much is this? This is 18 minus 19 by 19, which is 17. Oh wow. This is what is called as accuracy. Yes, it is. So atomic number, P. What I'm getting is P actually. So this is equal to P, right? So this is equal to P. Atomic number is 17. 17 atomic number. Do you recall what is 17? I remember noble gases. 18 is argon. 17 is 1 before argon. That's a halogen. That is chlorine, my dears. So I have Cl3717. That is the symbol of the atom. And ion is Cl minus. It's chloride ion. An ion with mass number 56 contains 3 units of positive charge. Okay. That means let us say that it is M3 plus 3 units of positive charge and 30.4% more neutrons than electrons. So say if the number of electrons is E, the number of neutrons is more, means you have added a sign plus. 30.4 per means divided by, cent means 100, so much. And I am also aware that this is plus 3, the number of electrons is number of protons minus 3. Please note, electrons are less than protons, and that is why I have plus 3 charge. Right? Now, I have atomic mass number is neutron plus proton. 56 is neutrons. Neutrons is 1.304 P minus 3 plus P, which is 2.304 minus 3.912. Wow. Therefore, P is 56 plus, that is 59.912 divided by 2.303. Well, looks very ravishing. Solve it out. How much does that give you? Now, one thing is for sure, number of protons has to be an integer. Even if you do approximate calculations, you would get an accurate answer, right? Shall we try that out? Yes, let us. 23 twos are, well, 23 twos is 46. So let us say this is 46 plus 13.912 divided by 2.3. Let me just do away with that 03. It's a stupid number. Right. It's 04 actually, not 3. 04. Whatever it is, we will neglect it. Fine. So how much is this? So P comes out to be 20 plus that 13.9. How do I judge this? 23 tens are 230, 5s is 23 into 6, 2, 3, 6 are 18, 12, 31, oh wow. So 23 6 is 13.8, yeah, 138. I have 139. Now I could say that 139 by 23 is very close to 6.0 something. So this is 26. Number of protons is 26. We are talking about iron. Wow. This is iron. Yes, it is iron 56, 26, 3 plus. And this, my dears, is the final answer. Arrange the following types of radiations in increasing order of frequency. Wow. A. Radiation from microwave oven. Well, that's microwaves are really long wavelength waves and low frequency. Amber light from traffic signal. If a light is visible, then that is obviously better off than radio waves. But then we are talking about amber light from traffic signals. Radiation from FM radio and cosmic rays from outer space, X-rays. Cosmic rays are the ones which have, minimum wavelength and maximum frequency. So yes, maximum frequency is cosmic rays, D. And then comes, see, these are very short wavelength rays, X-rays, which are very powerful. Then you have amber light from traffic signals. What is amber light? Is yellow light actually. So it is visible light, intermediate. So yes, then comes B. This is UV section, beyond ultraviolet. This is visible. And then if you have radio waves and microwaves, they have wavelength somewhere in millimeters. These have wavelength somewhere in angstrom units of, say, 6,000, 5,000 angstrom units, something like that. Microwaves have in mm. Radio waves are in meters. See. So wavelength goes on, increase. If you go on this side, wavelength increases and frequency decreases. So that, my dears, is the correct order of frequencies. Nitrogen laser produces a radiation at a wavelength of 337.1 nanometers. Okay. If the number of photons emitted is so many, calculate the power of this laser. Well, this is wavelength and this is the number of photons emitted. Can we just find out the energy of one radiation? Yes. E is hc by lambda 6.626 into 10 raised to minus 34 into 3 into 10 raised to 8 joule second into meters per second divided by lambda. How much is lambda? 337.1 into 10 raised to minus 9 meters. Lovely. This is energy of one photon. And there are so many photons. So total energy of photons, a laser, is this number multiplied by 5.6 into 10 raised to 24. 6.626 into 3 by 337.1. Now powers, let's collect the powers. 9 plus 8 is 17. 17 and 34, this is 10 raised to minus 17. And this multiplied by 5.6 into 10 raised to 24. fancy. How much is this? Let's see. Let's start cancelling one by one. Ugly numbers. 112.4 roughly 3 something that way, because that would be 11. 3 3s and 9, 10, 11 to 6, 7, something like that. 112 point, ugly numbers like this. Doesn't matter much. And so I have 6.626 into 5.6 by a loving 0.112367. 1, 2, 3 into 10 raised to 3. Fine. And 24 goes by this 21 into 10 raised to 4 joules. 1 upon 0.111 is 9 actually. Let's multiply these numbers and let's see what do we get. Well, do that, and this comes out to be 3.3 into 10 raised to 6 joules. Well, 330 kilojoules roughly. Actually, we were asked the power. I am not told that number of photons, this number of photons emitted is in what duration. If I just assume that this is per second, I repeat, this is not a part of question which is presented here, but if I assume this is per second, I would get so many joules per second. Very similar answer, but the answer has been changed to watts. Why? What? Why what here? The answer is changed to watts because we have assumed those many joules per second. That would give you the power. I'm not happy with the assumption, but there's nothing else to do. There we are. Neon gas is generally used in signboards. Okay. Now this question is based on simple Planck's quantum theory and one simple formula. If it emits strongly at 616 nanometers, okay, calculate the frequency of emission. First thing which I'm offered is that lambda is 616 nanometer, and I'm being asked frequency C is lambda nu. Therefore, nu is C by lambda. C, velocity of light, is 3 lakh kilometers per second. Divided by what is lambda? Lambda is 616 nanometer. Well, how much is that? I can happily and lovingly divide this. Can I? Well, I can, and this would give nano, means 10 raised to minus 9. So that is 3 by 0.616 into 10 raised to 14 hertz. And this happily gives you 4.87 into 10 raised to 14 hertz or per second. This is the first part, my dears, A, frequency of emission. And then we have part B, distance traveled. This is velocity into time. This is 3 lakh kilometers per second into 30 seconds. Well, that is 90 into 10 raised to 8 meters, or 9 into, if you want kilometers, kilometers will be 9 into 10 raised to 6 kilometers. Oh, that's quite some distance, I believe. Yes, 9 million kilometers light would have traveled in 30 seconds. But the question doesn't stop at this. They want still more dumb data. C, the energy of quantum. Now, E is h nu or hc by lambda. 6.626 into 10 raised to minus 34 into 3 into 10 raised to 8 joules meter divided by lambda. How much is the stupid lambda? Well, 616 nanometer. We just have to calculate this, whatever this dumb thing comes out to be. And so many joules would be the energy of each quantum. How much is that? Let's calculate and see. 17 and 34 times minus 17. That is fine. And what is this? 3 into 6.6 by 616. 0.03227. That looks ugly. So then this is 3.227 into 10 raised to minus 19 joules. This is the energy of every photon. Number of quanta present if it produces 2 joules of energy. One quantum has so much energy. How many quanta will give you 2 joules of energy? Number of quanta or number of photons. This would be equal to 2 joules divided by 3.227 into 10 minus 19 joules per photons. Ugly though it may be, this comes out with so many photons. And this would be somewhere around something into 10 raised to 18. And what is that something? We can easily discover on calculation. 6.2 looks like the number from a mathematical pre-calculated stuff. Can we again manage a rough number here? Yes, that's not very bad. 2 divided by 3.2. Now that is roughly 20 by 32. 20 by 32, 10 by 16, 1 by 16. That is roughly 0.6 something. So there, I think it fits in very well. Over and out. Over to the next question now. In astronomical observations, signals observed from distant stars are generally weak. Yes, they are. They're very far off naturally. A photon detector receives a total of so many joules from radiation of 600 nanometers. Okay, calculate the number of photons received by the detector. Let's take a look. Now, radiations are 600 nanometer. That means energy of every photon is hc by lambda, and lambda is 600 nanometer, we will see. And number of photons N is total energy divided by energy of one photon. That's lovely. Total energy is very weak, 3.15 into 10 is minus 18 joules only, oh my god. Divided by energy of one photon is hc by lambda, h 6.626 into 10 is to minus 34 joule second into 3.0 into 10 raised to 8 meters per second. Lambda is 600 nanometer, meter, joule, second goes off. Oh my god. What an onslaught. What do I get? I get, well, fun. 3 goes 200 times. And now I need to calculate, well, first the order of magnitude. 18 and 34, they give me 16, 10 is to 16, and this would be 10 is to minus 17. This is 10 is to minus 1, 2 zeros gone, 10 is to plus 1. That is 31.5 into 2, 1 0 adjusted here, divided by 6.626. Well, that sounds very interesting. Firstly, number of photons has to be an integer. So naturally, I should get some integer. This is the 63 by 6.626. Solve it and you get 9.508, which is really a ridiculous value. You can't have fractional photons, obviously. So it's either 9 or 10. If you want to just err on the happier side, you could say it's around 10 photons. Why not 9? Could be 9. I mean, at such a small number, it is governed by uncertainty also, but whatever. 10 is usually the number people assume, and that is the calculation. That's it. Lifetimes of the molecules in the excited states are often measured by using pulsed radiation source of duration nearly in the nanosecond range. Wow, this sounds very mysterious. This is all extra data. From the point of problem solving, it is just junk. Don't bother. You can start reading from here. If the radiation source has a duration of 2 nanoseconds, so there is a timing of 2 nanoseconds for which some radiation is being emitted. And the number of photons emitted during the pulse source is 2.5 into 10 raised to 15, okay, calculate the energy of the source. Well, so many photons are being emitted, fine. In this duration, okay. Now, I'm supposed to find the energy of the source. How do you think you can do that? Well, number of photons can be simply multiplied by the energy of each photon, and you would get the overall energy of the source. Now, in order to find the total energy of the source, my dear, you have to use E. Yeah. Total energy E is n times energy of one photon, which is n times h nu. Now, frequency is reciprocal of time period. Yes. So this is n times h by t. Yeah. N is 2.5 into 10 raised to 15, 6.626 into 10 raised to minus 34 joule second by, well, what is this time period? Time period would be 2 nanoseconds. So 2 into 10 raised to 9 minus 9 seconds. So many joules. Wow. And what does that come out to be? The energy of the source comes out to be 8.282 into 10 raised to minus 10 joules. The longest wavelength of doublet absorption transition is observed at 589 and 589.6 nanometers. Okay. Calculate the frequency of each transition and energy difference between two excited states. Now, the moment a student reads this, see, some students are immediately distracted by, oh my God, what is doublet absorption transition? We don't understand all that. Who cares? For the sake of problem solving, I mean, it's great if you understand. I'm not saying it's a bad thing. All it means is that two photons are being absorbed. That's it. And which are close in energy. Nothing more. But even if you don't understand the phrase, there is still a way you can solve the problem. All you're being asked is, you're given two lambdas. You're supposed to find out two frequencies and the difference in energy between them. That's it. Not a big deal. So, first of all, wavelengths lambda 1, lambda 2. Now, nu is C by lambda. Right? So, frequency is C, which is 3 into 10 raised to 8 meters per second divided by 589, or 3 into 10 raised to 8 meters per second divided by 589.6 nanometer. I mean, that does not look like much of a difference, and there is a minuscule difference only, but yes, you would get this is frequency 1, nu 1, and this would be nu 2, frequency 2. Okay. And energy difference, how will I calculate the energy difference? Delta E is E2 minus E1, which is H nu 2 minus nu 1, or nu 1 minus nu 2, whatever, that doesn't matter much. Fine. So, all I'm supposed to do is to find the difference between them, which is H C 1 by 589 minus 1 by 589.6 into 10 raised to minus 9, which goes up as 10 raised to plus 9. That's it. This is what you're supposed to do. Otherwise, just find frequencies, subtract them and multiply them by h, and you get the answer. What remains is a simple happy calculation. Frequency of transitions, if you calculate, well, nu 2 is this. Difference in energy comes out to be barely 3.3 into 10 to minus 22 joules, which is very, very small. What about nu 1? That's close by. I'll give you the answer. On calculating DS, nu 1 and nu 2, these are the answers. Nu 2 and nu 1. There we are. The work function for cesium atom is 1.9 electron volts. Threshold wavelength is expected, and what else is expected? Threshold frequency. Well, I guess that's not a magical thing. We can do that very easily. How? Work function is nothing but energy. So W naught is H nu naught, which is Hc by lambda naught. You can do whatever you like. I think I'll start with frequency. Threshold frequency is 1.9 electron volt. 1 electron volt is so many joules. Divided by H, 6.626 into 10 to the minus 34 joules second. God save us. What do we have? 1.9 into 1.6 by 6.626. 34 minus 19 is 15. Well, per second, which is so many hertz into 10 raised to 14. That would come out to be the order of magnitude. And this would be 16 fours are 64. That is about 4 point something it would be. 4.9, 4.8, something in that range. What is that here? 4.593. Let me write it down for you. 4.593 into 10 raised to 14 hertz. This is threshold frequency, right? What about threshold wavelength? Nu naught is C by lambda naught. Therefore, lambda naught will be 3 into 10 raised to 8 meters per second by divided by threshold frequency 4.593 into 10 raised to 14 per second. If I just approximate 3 and 4.5, that is 1 by 1.5, which is 0.67, 0.62 around 6 something into 10 raised to minus 6 meter or 6 point something something, 653 nanometers, 6.53. So let me come back. 0.653 if it is 653 nanometer. This is threshold wavelength for you. And then it says if cesium element is irradiated with a wavelength of 500 nanometers, calculate the kinetic energy and the velocity of ejected photoelectrons. More work. How do we do this? E kinetic. Yeah, Ke max is work function minus, energy of incident radiation minus work function. So, what is the energy of incident radiation? Let's find out. It is Hc by lambda minus Hc by lambda naught, something along those lines, right? 500 nanometers. Hc 1 upon 500 minus 1 upon 653 into 10 is to 9 per meter. Nano from up 10 is to minus 9, when it comes up it becomes 10 is to plus 9. What do I need to do? I just substitute and calculate and just have fun. Atomic structure is a very calculation intensive chapter. It would be very useful if you learn some quick random calculations. So this is accurately 6.626 into 3 into 10 is to minus 34 plus 8. 34 plus 8 makes it minus 26 joules second, joules into meter, yeah. And per meter will cancel away with that, into 10 is to 9 per meter, of course, goes off. This is 153 by 500 into 653. Loving calculation, I must say. How very emotional. This makes it, well, 26 3s are 78, 6 3s are 18, 19.88 into this ugly number. 153 forza would be 612, and this is 653. Around 41 more than that, 41. Now, this is 0.3 times roughly. So this would be how much? 4.3 around roughly. By around 4.3, And of course, that 500 is very much there. 10 is to minus 26. I take off this. That makes it minus 29 plus 9, 10 is to minus 20. How much is this? This is joules. Such a wondrous change. Let me say this is around 20. No, 40. 40 by 4.3. A little less than 40 divided by 4.3. That would be around 9. Roughly 9 into 10 is to minus 20 joules. Roughly. This looks like the kinetic energy of photoelectrons. Let's check the number. 9.3 into 10 to the minus 20. After a lot of jumps, we are reasonably close. 9.3. Well, I like that. What I'm trying to do is, don't use calculator always. At least try to do rough calculations so that you know that you're getting close to this answer. Many times in exams, it's a very useful technique. Lastly, we have to find the velocity of ejected photoelectron. Wow, how do we find that? Very easy. Half mv square is K max. So V is under root kinetic energy into 2 by m. Right? We know the kinetic energy, 9.3 into 10 minus 20 joules into 2 by mass of electron is 9.1 into 10 minus 31 kg. Substitute, calculate and get the answer. Let's do that. Major part is calculation and being able to do this correctly. That was 9.3 into 10 to minus 20 joules divided by mass, which is 9.1 into 10 to minus 31 kilograms. Fanciful. This is a little more than 1 into 2, whatever that comes out to be. And there is more ugliness. 10 is to 11. So this is going to be around 22 point something into 10 into 10 is to 10. Around 21, 22 roughly, that's the number. Right? A little more than this is 2 point something into 10. Now please note 9.3 by 9.1 will be 1.0 something. That square root will be still smaller. So I assume that, say this is roughly around 2.05. If this is the case, I would have around 20.5 into 10 is to minus 10, plus 10, sorry. You leave it out. Root of 20.5. 16's root is 4. What about 4.5? 4.5 square root is 20.5. Yes, roughly. Yeah. So 4.5 into 10 is to 5 meters per second. We are very close. 4.5 to good enough. Good enough. This is what we get. One more question from photoelectric effect, and that says, following results are observed when sodium metal is irradiated with different wavelengths. Fascinating. Calculate the threshold wavelength and, oh my God, the Planck's constant. Actually, this is also how Planck's constant was experimentally estimated. And what is it? I'm given incident radiation wavelengths, and I'm also given the kinetic energies of ejected photoelectrons. Well, how do we do this? Ke max, we know that. Ke max, which is half mv square. This is hc by lambda minus hc by lambda naught. Fine. What do I know? I am given velocity v, I am given lambda. I am not given lambda naught, of course. I am not given h. I can shamelessly assume c, I believe. Velocity of light and even mass of electron for that matter are known things. I just substitute, I get equations. As a matter of fact, I'll get 3 equations because I've given 3 data. I could use just 2 and solve them. Or even better, if you're willing to find out mass of electron as a variable, you could actually use that also here. You have 3 equations, 3 unknowns, solve them. Whichever you feel happy. I have no intentions of going unnecessarily long. Mass of electron and velocity of light, I'm going to assume. Just any of these 2 data you can substitute, solve and get the answer. Like, please note, nanometers, this is the wavelength, and when you are given V into 10 to minus 5 is so many, that means I'll just give you this example. That means it means V is equal to 5.35 into 10 to 5 centimeters per second, or 5.35 into 10 to 3 meters per second. This is how you should calculate the velocity. Okay. I have the velocity, I have lambdas. I'll just substitute in one case and show you. Half into m. Now I could just divide by c, right? The mass of electron is 9.1 into 10 to minus 31 kg, and velocity of light is 3 lakh kilometers per second. Fine. V square is 5.35 into 10 to 3, the whole squares, meters per second, of course, meter square per second square, no doubt. Now, the 1 meter per second will cancel from here. 1 by lambda minus 1 by lambda naught. This is h, 1 by lambda. This is 400 minus 1 by lambda naught, which is threshold wavelength. I can calculate all this ugly number. Yes, I have one equation. Lambda naught, lambda 1 naught, like this. Right? Please note, I could also do a similar calculation. I can have the same thing, half into 9.1 into 10 to minus 31 upon 3 into 10 to 8, ugly numbers. I could have second velocity. This is 4.35 into 10 to 3 meters per second, which is h. Now I'm using this 1 by 450 minus 1 by lambda 2 naught. As a matter of fact, there is no lambda 1 naught or 2 naught. Why? This is just sodium metal always. The threshold frequency doesn't change. Velocity changes with incident radiation, which is anyway changing. I have two loving equations and I have two lovely unknowns. Can I not solve them? Yes, I can. And the moment I do, well, I get the answer. I get answer for both Planck's constant h and threshold frequency lambda. What does that come out to be? Threshold wavelength comes out to be 531 nanometers. Planck's constant is our good old 6.6 into 10 minus 34 joule second. The ejection of photoelectrons from silver metal in the photoelectric effect experiment, okay, can be stopped by applying a voltage of 0.35 volts. It is given that stopping potential is 0.35 volts. Are you aware that this will give you maximum kinetic energy of photoelectrons ejected? So therefore, Ke max of photoelectrons is 0.35 electron volts. Whatever is the voltage of stopping potential, same is the electron volts energy of ejected photoelectrons, the maximum kinetic energy, right? And we know that by Einstein's photoelectric equation, Ke max is hc by lambda minus work function. Work function I am supposed to find. Well, hc by lambda, I guess I know that c by lambda. How much is this going to be? 256.7 nanometer E. If you remember, hc by lambda, if you want this in electron volts, we had a short trick also. 1 2 ka 424 by 2567 angstrom units. If you remember, so many electron volts. If I calculate this, I would get the correct electron volts. And how much would this come out to be? This 12424. Now, if it is 124.4 into 2, this is 24848, 2484, 2567, a little more. So if I just cancel this, the denominator is a little more than 0.2. A little more. How much? 2484, 2567, not even 100. 80, it's around 80 more. Negligible. This is approximately 1 by, what do I say, 20? 0.2. 1 by 0.2. That should be around 5 electron volts. If I do more accurate, it would be, the denominator is actually a little more than 0.2. So it would be 4.9, somewhere around that. That would be the energy of incident photoelectron. What about the work function? Work function W naught will be Hc by lambda minus 0.35 electron volts. This is around 4.9 minus 0.35. How much does that come out to be? Oh, that's pretty huge. 4.55 electron volts. It's a very rough, quick calculation. If we check, 4.48 is the accurate one, and 4.55 we have managed as an approximate answer. Not very bad actually. We did a very major jump and very approximate calculation, and still I think we have managed reasonably well. Method is this. Calculator answer is, of course, 4.48 electron volts. If the photon of wavelength 150 picometer strikes an atom and one of its inner bound electrons is ejected out, not surface one, with a velocity of so much, calculate the energy with which it is bound to the nucleus. Well, very, very interesting. I have energy of incident radiation is 150 picometer, right? And it is striking not a crystal but just an atom, fine. And kinetic energy of ejected photoelectron is not kinetic, it's velocity. This is half mv square, and v is 1.5 into 10 raised to 7 meters per second, very high, very, very high. Calculate the energy with which it is bound to the nucleus. The concept is very similar to photoelectric effect, although instead of metal crystal, it is being applied to an atom. How do we first use common sense and derive our equation? It is E incident photon. This is the energy of photon which came in minus energy with which it is, electron is bound to nucleus, or the binding energy of electron. This is equal to Ke of ejected electron, right? Incident photon, Hc by lambda, minus energy bound, this we have to calculate, is half mv square. Mass of electron I know, velocity of electron I have been given. I just have to substitute and I will get the binding energy. How do I do that? Let me do that for you. It is, first of all, let's just calculate them one by one. Units you can choose, will it be electron volts or will it be joules? I prefer on an atomic number scale. I mean, if you're dealing with atoms, molecules, photons, electron volts is a much more convenient unit. We can take that. So E incident, Hc by lambda, which is 12424 electron volt angstrom units by, what do we have? We have 150 picometer, that means 1.5 angstrom units. This cancels off. I'll get something, I'll get a number. So many electron volts, and this is going to be very huge. How much? Well, this would be 12424, 24, 15 8s are 120, 42, 15 3s are, no, sorry, 15 2s are 30, 124, 15 8s are 120, 40, 15, roughly 3. So, 12424, 8, 12,000 comes to be roughly. This is roughly what you get. It is 2.67 whatever, you get 82, 83 electron volts nearly. This is the energy of photon which is striking the atom. Kinetic energy, yes, it goes out with this kinetic energy. How much is this? Ke is half mv square 9.1 into 10 raised to minus 31 kg into velocity. Let us square it. 1.5 square is 2.25 into 10 raised to 14 meter square per second square. Huge, huge, huge. Not that huge actually. This is in joules. If you wish to convert this to electron volts, yes, 9.1 into 2.25 by 2 into 1.6. 31 minus 14 would be 10 raised to minus 17 divided by 10 raised to minus 19. So many electron volts. Oh my God. Can we calculate that? Yes, why not? Yes, we shall. And yes, we can. Something into, what is that something? We'll need to calculate that, of course, into 10 raised to 2 electron volts. Can we have an approximate number? We can. But why go for approximation when it can be more accurate? We'll do that. 6.4, this would give you, or this is around 640 electron volt. Well, 640 is what you have to subtract. 3 out of this 4, 6, 76, 43 electron volts. This is a rough number which comes out. In case we do a more accurate calculation, maybe a little difference of that 32, 43, around 11 electron volts, we can sort it out. So these are the answers, very close. I mean, you might feel that there's a little difference. Percentage difference is very small, reasonably accurate, a beautiful answer. Emissions from partial series end at orbit n is equal to 3, okay, and they start from orbit n and can be represented as nu is equal to 3.29 into 15 hertz. Some formula has been given. 3.29 into 10 is to 15 hertz. 1 by 3 square minus 1 by n square. Calculate the value of n. If the transition is observed at 1285 nanometer, find the region of the spectrum. The lambda of what is observed is 1285 nanometer. Now this is frequency nu. Let us multiply by Planck's constant h. I have h nu. H nu is, well, hc by lambda. Yes. Therefore, I could say 1 by lambda is 3.29 into 10 is to 15 upon 3 into 10 is to 8. This is per second and this is meters per second. Oh my God. 1 by 3 square minus 1 by n square. Wonderful. And how much is this? This lambda comes out to be, I'm given 1285 nanometer. This is 1285. Therefore, 1 upon 3 square minus 1 upon n square is what this ugly number comes out to be. 3 into 10 raised to 8, 8 and 15 by 3.29 into 10 raised to 15 into, how much is lambda? 1285 into 10 raised to minus 9. Right? All I'm supposed to do is to do the calculations, check this out, and find out the value of n. And let's see what it comes out to be. On solving, do this happily. You can actually do it by head and trial also, and you would see that n comes out to be 5. Solve this and lovingly get the value of n. That means the transition is from 5 to 3. Obviously, partial series is in, they're saying find the region of the spectrum. It is the infrared region of the spectrum. N is 5 and it is infrared. Calculate the wavelength of the emission. This is again from Bohr's theory. Spectrum. Emission transition, if it starts from orbit, okay, having a radius, R initial is 1.3225 nanometers, okay, and as it falls final radius is 211.6 picometer. Oh my God. Name the series to which this transition belongs and the region of the spectrum. We are assuming this to be hydrogen atom. It seems nothing else has been mentioned. We are shameless enough to assume this as hydrogen. What do we do? Well, we are given radii. Yes. And what does radius have to do with any other data? Can we have some idea, some inkling? Yes, electron can revolve only in those orbits for which circumference is integer multiple of lambda. I mean, we could use that in case you feel like. Otherwise, we can simply say that using the radii, we can calculate. Once we are aware of this is the radius, we can calculate n, this is the value of n, and accordingly we could get the transition. R is R naught n square by z, and since z we are assuming as 1, R by R naught is n square. So what R initial? What is R initial? It is 1.3225, okay, by R naught. R naught is 0.53 angstrom unit, या 0.0529 nanometers for hydrogen atom. 0.529 angstrom units is radius of first Bohr orbit. We use that. How much does that come out to be? Well, looks like 4. If I just multiply 0.53 by 4, 4 is at 12, 21. No, not really. So, that 4 doesn't look like a good number. Let's try 5. 5 is a 15. 5 is 20. Yeah. So, this looks like 25, which is also equal to n square. And n initial is root 25, which is 5. This gives me that the electron was initially present in n is equal to 5. Wow. That's convenient. That's cool actually. Similarly, R final by R naught. And how much is that? It's so many picometers, 2.116. 2.116 angstrom units divided by 0.53 angstrom units, which is R naught. Now what I see is 5 4s are 20. This looks like 4, which is n final square. Therefore, n final looks like 2. Wow. So from fifth shell, electron is actually falling to second shell. This is Balmer transition. If it is Balmer transition, which is the spectrum? This is the visible region. How do I know this? Electrons from anywhere, if they fall in n is equal to 2, they represent Balmer series, and Balmer series very well lies in the visible spectrum, right? So, the series to which this transition belongs, we don't have to calculate anything else anyways. The moment I see n is equal to 2, it is Balmer series, and that ends it. There we are. Oh no, we also had the wavelength. Let's calculate wavelength. That's not very difficult. How do I get that? 1 by lambda is RH, 1 by 2 square minus 1 by 5 square. We use Rydberg's formula, and RH is 1.097 into 10 raised to 7 per meter. 1.09 into 10 raised per meter. Can we do that? Of course, nobody can stop us. This is 1 by 4 minus 1 by 25. 25 minus 4, 21 by 4 into 25. That's lovely. As lovely as it gets. Therefore, lambda is 100 by 21 into 1.09 into 10 raised to minus 7 meters. Lovely. Solve that. That comes out to be 434 nanometer, or roughly 4,300 angstrom units, which is Balmer region or visible region very obviously. And this one goes with de Broglie equation. It says, dual behavior of matter proposed by de Broglie led to the discovery of electron microscope, often used for highly magnified images of biological molecules and other types of materials. Loving though this is, it's all junk. This is one piece of question which is just irrelevant. If the velocity of electron is so much, I'm given velocity of electron as 1.6 into 10 raised to 6 meters per second. Calculate the de Broglie wavelength lambda associated with this. Lambda is h by p, h by mv. Oh my God. Very often electrons are used. So let me just see, this is 6.626 into 10 raised to minus 34 joule seconds divided by 9.1 into 10 raised to minus 31 kilograms into velocity. Just for the sake of convenience, let us say if the velocity was 10 raised to 6 meters per second. That's a lie. I know it's a lie. It is 1.6 times. We'll see that. We'll handle that. Just stay with me. I just want to calculate a shortcut for you so that each time you're not harassed with these calculations. These calculations come across you very often. Let me divide them and get you a number. First of all, 31, 34, that's 10 minus 3, 10 minus 6, that makes it 6.626 by 9.1, loving though this is, and this into 10 raised to minus 9. Yeah, 0.91 if I take this into 10 raised to minus 8 meters. Right? This is a number which I tend to get by, you could say, some number V0. What is V0? V0 is velocity upon 10 raised to 6. I've used already 10 raised to 6 because roughly this is the range or the order of magnitude for which you will normally encounter the velocity of electron. I just divide this and let you know the number. This, if you see, this is 728. Yeah, 7.28 into 10 raised to minus 8 upon V0 meters. If you find this ugly, I would suggest that 10 raised to minus, just convert it to 10 raised to minus 9, so you will have nanometers, right? So that would be 0.728 upon V0 nanometers. This should be your answer. Now, in our case, V0 is 1.6. So our answer, if you want to use this as general formula for de Broglie wavelength of electrons, you can save some bit of calculation. If you are confused, let me repeat. Very often, de Broglie wavelength of electrons is expected. Mass of electron is fixed, Planck's constant is fixed. So I am suggesting that de Broglie wavelength of electron, you just remember with calculation, this is 0.728 nanometers by V0. And what is V0? V0 is velocity of electron upon 10 to the power 6. Usually when you are encountering such electrons, they often have velocities in terms of 10 raised to 6 meters per second. SI units, of course. You take them, you substitute this, and without having to do all these calculations, you will directly get the answer. If you have energy to remember it, mark it up. In our case, the answer would be just 0.728 divided by 1.6 nanometers. How much does that come out to be? 16 4s are 64. So 16 4s are 64. Sorry, this will be 0.4. Then 72, that means 88. 16 5s are 80. 0.455 electron. See, 0.455 nanometer. So, even less than a nanometer, the de Broglie wavelength associated with this electron is 0.455 nanometers, or if you want picometers, 455 multiplied by 1000, 455 picometers. Very small. Similar to electron diffraction, neutron diffraction microscope is also used for the determination of structure of molecules. Okay. If the wavelength used here is 800 picometers, calculate the characteristic velocity associated with the neutron. How do we do this? This sounds, well, ugly enough. It is. It's just calculation, but nonetheless, let's do that. We have de Broglie wavelength as 800 picometers. Yes. Velocity. Now, please note, this is h by mv. Therefore, velocity of neutron will be h by mass of neutron into lambda de Broglie, 6.626 into 10 raised to minus 34 joules second, divided by mass of neutron into de Broglie wavelength. The stupid wavelength is 800 picometers. So much. All I need to do is to put the mass of neutron and do the calculations. Neutron is 1.674 into 10 raised to minus 27 kgs. Yes. Do this fanciful calculation, and exciting though this is, it comes out to be, well, 494 meters per second. Good enough. Around 500 meters per second. This is the velocity of neutrons. If the velocity of electron in first Bohr orbit is 2.19 into 10 raised to 6 meters per second, which is actually the velocity in first Bohr orbit of hydrogen atom, calculate the de Broglie wavelength associated with it. How do we do that? Well, there are two methods. One is use the standard thing. De Broglie wavelength, lambda de Broglie, is h by mv. And we just derived, in case you remember, I have suggested you a calculation also for just electrons purposes. In case electron has a velocity v naught, which is 2.19 in this case into 10 raised to 6 meters per second. And usually electrons are given velocities as multiple of something into 10 raised to 6 meters per second. This calculation is best done like this. This is 0.728 nanometer by v naught. And v naught is something into, this, whatever is the velocity, velocity divided by 10 raised to 6 is equal to v naught. So in our case, it is 2.19. So 0.728 upon 2.19 nanometers. Wow, what is this? That's it. This is the de Broglie wavelength associated. Is it difficult? Not really. And this in solving comes out to be 332 picometers. And please remember, this is also nothing but circumference of the first Bohr orbit. There is a second method. If you just remember the circumference of first Bohr orbit, that is simply 332 picometers. The velocity associated with the proton moving in a potential difference of 1000 volts is so much. Okay. If the hockey ball of mass 0.1 kg is moving with this velocity, calculate the wavelength associated with this velocity. Observe that this question has a lot of drama. You are given proton, unnecessarily you are given this potential difference of 1000 volt, which is just given to confuse you. It has no relation. I am just given the velocity of proton is so much, and same is the velocity of hockey ball. So I just know that velocity of hockey ball is how much? 4.37 into 10 raised to 5 meters per second, which is like pretty high. And mass of hockey ball is 0.1 kg. De Broglie wavelength of hockey ball will be h by p, which is h by mv, which is 6.626 into 10 raised minus 34 joules second divided by 0.1 kg into the stupid number. What is this? 4.37 into 10 raised to 5 meters per second. That's it. That's it. This would give you your nice, loving and happy de Broglie wavelength, which is bound to be very, very small. How small? Actually, you would calculate this number to be 1.5 into 10 raised to minus 28 meters. Truly, truly so small, it's practically negligible. And there comes our old and haunting Heisenberg. If the position of electron is measured with an accuracy of plus minus 0.002 nanometer, right? So I'm given delta x is 0.002 nanometers. Calculate the uncertainty in the momentum of electron. Now delta p is question mark. Suppose the momentum of electron is h by 4 pi. into 0.05 nanometers. Is there any problem in defining this value? You remember Heisenberg's principle? Yes. From there we have a formula. What is that? Uncertainty into momentum into uncertainty in position is greater than or equal to h cut by 2. And h cut is how much? This is h by 4 pi. In limiting case, it may be equal to h by 4 pi. Right? Right. All we need to do is to just substitute. I'm given delta p, the uncertainty in position, your delta x. I'm supposed to find delta p, right? So delta p into 0.002 nanometers is so much. In the limiting case, we just use equality. So delta p is greater than or equal to h, 6.626 into 10 is minus 34 joule second divided by 4 into 3.142 into 0.002 nanometer, which is so many meters. So good looking it is. How much will this boil down to? You can calculate that. This would give you 2.637 into 10 to the minus 23 kilograms meters per second. SI units of momentum, 2.637 into 10 to the minus 23 kg meters per second. This is the uncertainty in momentum. Okay, this is fun answer. Now comes the second part. Suppose the momentum of electron is h by 4 pi into 0.05 nanometer. Please look at the units. Units of momentum is not nanometer. So actually this is, they're saying P is h by 4 pi into, this should be in denominator, 0.05 nanometer. This is what they're saying. It appears as if this is separate and this is separate. No. Assume this in denominator. Then it would work. Say P is so much, right? Is there any problem in defining this value? They're asking. We have found uncertainty in momentum. They're saying this is uncertainty, fine. But what is the momentum? Momentum is so much. Delta P, we just found, is h by 4 pi into 1 upon 0.005 nanometer it was. Right? No, 0.002 nanometer. Okay. Can I take a ratio? I very well can. If I take a ratio, P by delta P, this comes out to be how much? This comes out to be 0.05, 0.002. So delta P by P is 25. What does that mean? It means that if momentum has certain value, uncertainty is 25 times the momentum itself. That sounds very stupid. Say my height is, say, around 5 feet, 5.5 feet, 6 feet, say, for example. It's not 6 feet, less, but assume. Now I say my height is 6 feet. Somebody is trying to measure, and he says that your height is not 6 feet. It could be, he could be measuring anywhere between 6 feet to 150 feet. 150 feet is taller than the building itself. It's too much. I mean, so many stories, 15-storied building. I'm of course not as tall as 15-story building, god damn it. But if that is the kind of uncertainty which somebody is saying, that momentum may have a certain value, but the uncertainty, the error in the momentum may be 25 times the actual value, the correct value. That means that calculation is absurd. That measurement is very stupid, very, very inaccurate. So when they are saying, is there any problem in defining this value? There is a problem. You have tried to make the position so accurate. The problem is the uncertainty in momentum has become absurdly large. So actually trying to measure momentum is meaningless. That is the problem associated with this measurement. The quantum numbers of 6 electrons are given. Arrange them in the order of increasing energies. If any of these have same energy, let's see. N4L2. Now, energy is largely decided by S and P orbital only. ML and S, no. This is a 4D orbital. This is 3D. This is 4P. This is 3D again. this is 4, no, I'm sorry, this is 3p and this is 4p. Now there are offers that I have to discover the order of their energies. Can I arrange them? I could actually. You remember our Gauss principle? Yes. 1s2, 2s2, 3p, 2p6, 3s2, 3p6, 4s2, 3d10. In that order it used to go, if you remember. I could just draw this for you. 1s, 2s, 2p, 3s, 3p, 3d, 4s, 4p, 4d. This was the order. Now since I don't have anything extra, I'll not try more. What I mean is 3p, 4s, then 3d, 4p. 3p, then 4s, then 3d, then 4p, then 5s, then 4d. This is the order, right? So if I have 4d, 4d is bound to be highest of all. How many 4ds are there? Only one. The first one. So that has the highest energy. Increasing energies, the 1 would be the highest. I'll see. And the minimum would be 3p. Do I have 3p? Yes, I have 3p. 3p is the minimum. So what is this? 3p is 5th. So 5 is the minimum. First one is the maximum. We have 3d, 3d and 4p, 4p being repeated. Now 4p is bigger than 3d. So 4p and 4p will come here. 4p and 4p. I'll need one more bracket, I believe. And then would come 3d and 3d. 4p is 3rd and 6. So 3 and 6 will figure out somewhere here, right? And 3d, ml1 and 3d, ml minus 2. All d orbitals are degenerate, they have same energy. So 2 and 4, both of them are 3d, yes, and both of them have same energy. But it is less than 4p. One of them has ml0, one of them has ml0. Only spin difference, no difference. In fact, they are the same. 4l1, ml0, s half. Yes, 3 same as 6. 4p, 4p. 3 is same as the 6th one. Right? There we are. 5 is least, 2 same as 4, 3 same as 6, and 1 is the maximum. This is the correct order of energies of the orbitals. The bromine atom possesses 35 electrons. Okay. It contains 6 electrons in 2p orbital. Fine. It has 2p6. That is not a wonder. 6 electrons in 3p. Okay. And 5 electrons in 4p. Which of these electrons experiences the lowest effective nuclear charge? The lowest effective nuclear charge, my dear, is experienced by the outermost electrons. Why? Because nucleus always has same protons. As between the nucleus and your electron, if more and more shells come, that means more and more extra electrons are inside, and greater the number of electrons inside a shell, lesser is the effective nuclear charge, which is experienced by the outer electron. So outermost electrons actually experience the least or the minimum effective nuclear charge. So lowest effective nuclear charge is experienced by 4p, 5 electrons. Amongst the following pair of orbitals, which orbital will experience the larger effective nuclear charge? Let's take a look. 2s and 3s. 2s, the inner ones, experience larger Z effective. 4d and 4f. D orbitals are inner as compared to F orbitals. So yes, the effective, they experience greater effective nuclear charge. 3d and 3p, p orbitals like S experiences it more strongly than p, p than d, d than f. if n is, say, for same principal quantum number, this is the order of experiencing effective nuclear charge. The unpaired electrons in aluminum and silicon are present in 3p orbital. Okay, which electrons will experience more effective nuclear charge from the nucleus? Well, aluminium and silicon. Please understand, as we move across a period, number of protons in the nucleus increases, and although electrons also increase, they are never able to shield the nuclear charge as effectively as the increase in number of protons. So always, if you're moving across a period, Z effective increases. So although aluminum and silicon both have 3p electrons, silicon would experience more effective nuclear charge. So silicon is the answer? Yes, silicon is our answer. And that is why atomic radius also decreases because of greater attraction. Indicate the number of unpaired electrons in phosphorus, silicon, chromium, iron and krypton. Well, phosphorus electronic configuration is neon 3s2 3p3. Neon 3s2 3p3. And what is that? This is 3s2 and this is 3p3. Fine. The number of unpaired electrons is? It is 3. This is A part. B part, silicon. Neon 3s2 3p2. So number of unpaired electrons is 2. You can just draw the electronic configuration and get that. That's very simple. What about chromium? Chromium is very interesting. Chromium is argon 3d54s1. Why? Extra stability of half-filled d orbital motivates a departure from regularity. 1, 2, 3, 4, 5, 3d, 4s. You have 6 unpaired electrons in chromium. Oh my God. What about iron? Iron. This is C part. Then D part we have iron. Iron is 3d6, 4s2, 1, 2, 3, 4, 5, 6. It has 4 unpaired electrons, as you can see. You can count these are single electrons or unpaired electrons. And E, krypton, noble gases are fully filled. They have 0. Why? It is 4s2, 4p6, 3d10. This is the case of krypton. All the electron shells are fully filled, everything is paired, and there is no unpaired electron in case of krypton atom. Not potassium, it is krypton atom. How many subshells are associated with n is equal to 4? Well, n is equal to 4. It has 4s, 4p, 4d, and 4f. It has 4 types of subshells. But the question is not types. The question is the number of subshells. 1, 3, 5, and 7. Just add this up. This looks like 16. 16 subshells are associated with n is equal to 4. How many electrons will be present in the subshells having ms values of -12 for n is equal to 4? Now, there are 16 subshells, and every subshell can have only 1 electron with spin -12, right? So, since every subshell can have only 1 electron, again, there will be 16 electrons which will have spin quantum number -12. If you count everything which is filled in, n is equal to 4. 16 is the answer. So, dears, this marks the conclusion of the discussion of NCERT questions of atomic structure. Pretty long, pretty vivid, and pretty diverse. But then, as I suggest, atomic structure is a chapter of calculations. You have to do lots and lots of calculation practice, and this practice actually gives you a good fluency in solving problems of physical chemistry for future chapters also. In that sense, it is a very good practice. If you want to learn atomic structure in a more deep way, If you want to learn it via theory, all the complete details, you're welcome to visit the website of or the app of Vyas Certification. Download the app, access my lectures, and well, join a course of academic structure. All the best. Have a great time.